We're talking about something called physical vapor deposition. Seriously? Have you ever wondered about that? You know, that flawless, almost liquid metal look on a brand new smartphone? Or the deep, rich color on a luxury watch that just refuses to scratch or fade, ever? It's not paint. And it's definitely not just shiny metal. Nope. It's something way, way cooler. The answer is basically a layer of invisible armor. It's a microscopic coating that gives these objects incredible strength and that amazing look. So, let's pull back the curtain and see how it's done. So, what is PVD really? Well, at its core, physical vapor deposition is kind of like spray painting, but on an atomic level. Imagine you could take a solid chunk of some ultra-hard material, turn it into a gas, and then let that gas settle back down onto an object atom by atom, forming a perfect, super thin skin. That's pretty much PVD in a nutshell. It all boils down to three main steps. First, you've got to turn your coating material into a vapor. Then, and this is key, this all happens inside a vacuum chamber. Why a vacuum? Because with no air in the way, the vapor can travel in a perfectly straight line. Finally, when that hot vapor hits the cooler object you want to coat, we call that the substrate, it instantly cools and solidifies, creating that flawless, thin film coating. But here's the thing, getting that level of perfection, well, it's not cheap and it's not easy. PVD is really a classic story of getting these incredible benefits, but they come with some pretty big real-world limitations. It's all about the trade-off. And this table really lays it all out, doesn't it? The upsides are just amazing. You get coatings that are ridiculously hard, resist corrosion, and the whole process is way better for the environment than old-school electroplating. But the downsides are serious. It's a line-of-sight process, meaning it struggles with complex shapes. The gear is super expensive, you need massive cooling systems, and you better have some highly skilled people running the machine. It's a high-stakes game, for sure. So let's dig into that very first step, making the vapor. Because how you turn that solid material into a gas is actually what separates the different types of PVD from each other. Yep, pretty much everything comes down to this one question. Are you going to heat the material up until it just boils away into a vapor, or are you going to get aggressive and just blast it into atoms? The answer to that question changes everything. The cost, the complexity, and what kind of stuff you can coat. Okay, so here are the two big philosophies. On one side, you've got thermal evaporation. This is the simple approach. You basically just heat up your material with a filament inside the vacuum until it evaporates, kind of like boiling a pot of water. It's cheap and it's simple, but it only works for materials that have a low melting point. Now, on the other side, you've got sputtering. This is the blasting method. You fire high-energy ions at your material. Think of them like microscopic cannonballs, and they physically knock the atoms loose. It's way more complex, and yeah, it's more expensive, but the huge plus is that you can do this with super tough, high melting point materials like ceramics. You know, this brings up a really interesting question. We're talking about adding layers of material that are just a few atoms thick. How on earth do you control something that precise? I mean, you can't exactly check it with a measuring tape, right? Well, the solution is just brilliant. The secret weapon is a little device called a quartz crystal microbalance, or QCM. It works with a tiny piece of quartz crystal that vibrates at an incredibly stable frequency. As atoms from the vapor land and stick to the crystal, they add a tiny bit of mass. That extra weight changes the vibration ever so slightly. The QCM is so sensitive it can detect these tiny shifts, letting the operators know exactly how thick the coating is in real time. It's absolutely mind-blowing precision. Okay, so now we get the basic ideas and the trade-offs. Let's try to apply this stuff to a real-world problem. All right, time for a little scenario. Your job is to put a perfect wear-resistant coating on this gorgeous watch case. But look at it. It's not flat. It's got curves, nooks, crannies, all kinds of complex angles. So, which PVD method are you going to pick to get the job done right? Well, we can start by figuring out what won't work. Right off the bat, thermal evaporation is out. Another similar one, electron beam PVD, is out too. Why? Remember that line of sight problem we talked about? The vapor just travels in a straight line, so there's no way it can get into all those curves and corners evenly. You'd get an inconsistent mess. We can also roll out a really cool new method, pulsed laser deposition. It's got potential, but it's just not quite ready for prime time yet. And that leaves us with our winner, sputtering. Because the atoms are literally blasted off the source material, they scatter in all directions inside the chamber. This means they can find their way onto all those complex, non-flat surfaces much more evenly. It's what makes it the go-to method for things like high-end jewelry and luxury watches, where every single millimeter needs to be perfect.